Hey everybody, my name is Tess Weidenkopf. I'm actually a junior here at Roanoke College, a double major in biochemistry and theater, and I'm on pre-med track as well. So I'm here to talk to you all about the research I do on campus with Dr. Hughes, and it's CIS Nanocrystal Toxicology. So first off, I'm going to give you all a little bit of background information on what exactly are nanocrystals. What are quantum dots? Well, they're little tiny structures that are composed of a core, a shell, and a stabilizing ligand. The core is your main material. For example, in my research, we use copper indium as our core. The shell is something that stabilizes the fluorescent, and then the stabilizing ligand is what makes your nanocrystal soluble in a very specific environment. So say you want it to be an aqueous, soluble in an aqueous solution, you would have an aqueous stabilizing ligand on the outside, as you can see actually in the picture on the bottom right. That is a little bit of a picture of the composition of what a nanocrystal looks like in an animated slide as well. So one reason that I put Tony Stark on here is that one scene in the Avengers Endgame when he pulls on his drawstrings on his jacket and then his suit just comes out of nowhere. What he's using there is nanocrystal technology. So that just gives you a little bit of example of all the cool things that nanocrystals can do. So a little bit more background, quantum dots have very distinctive optical properties. That's why in like the past 20 years, they've been super influential, especially in biomedical research, and people have been looking and doing a lot more research on them. They're very popular. So they're characterized by their band gap energy, and a band gap energy is the difference between your HOMO, which is your highest occupied molecular orbital, and your LUMO, which is your lowest unoccupied molecular orbital. And you can see actually in the diagram on the very bottom, that just goes a little bit about conduction bands and the valence bands as well. So basically what happens is an electron gets excited up from the HOMO to the LUMO, and then when it falls back down, it emits a fluorescence. So another cool optical property about nanocrystals is that a lot of them fluoresce. So some of the applications of nanocrystals are that they're used in solar conversion, LED display, lighting, and also biolabeling. So what is toxicology? I'm going to get at my main research question here as well. So, toxicology is the science concerned with the effects of nature and also the detection of poison. So quantum dot toxicity in the environment is something that's very important, obviously, because our environment is going through a lot of environmental change, sped up a lot by different technologies humans create, and that's changing our environment and causing it to it's causing it to collapse. So basically, how do quantum dots relate in this toxicity, and how do they contribute to the toxicity in the environment? So basically, nanomaterials enter the environment through waste treatment. So any specific nanomaterials developed to develop new technologies, they get into the waste system, and then they enter into the riverbeds. And when they enter into the riverbeds, they go into the soil of these riverbeds, and the shell degrades, and the core, which is the problem, which are your heavy metals normally, they're released into the environment, and then they're reabsorbed in humans. And this can either be through, if it's a freshwater lake, that's water you're drinking after it's been purified, but it's still in that water. It's also killing fish, like tons of fish are being killed because they're having this constant exposure to these heavy metals. And so what exactly is the problem with this? How does it hurt a human if you're exposed to heavy metals for a long period of time? So one of the biggest contributors is actually cadmium. And cadmium is used in a bunch of nanocrystals. It's pretty versatile, but it's first off, it's massively expensive. And also it can affect your bones, liver, kidney, lungs, your brain as well. If you have a lot of exposure to them, it can start to deteriorate them. So basically, my research and my main research question is the characterization of the nanocrystal copper indium sulfide, or CIS, toxicity using Danio rareo, which are zebrafish. So some techniques I use in lab, I use the synthesis of nanocrystals, UV vis spectrometry, ligand exchange, size exclusion chromatography, and I also breed my own fish, which are a bunch of cool things. If you can see the bottom left picture, that's a picture of a zebrafish. That's just kind of their little basic anatomy there. The middle picture is actually the synthesis of the very initial synthesis of my CIS nanocrystals, and that's the hood I work in. And then on the very far right, that is just some UV vis spectrometry I do in order to characterize the concentration of my nanocrystals. So going to go in the materials and methods a little bit. So I synthesize CIS from copper-1, indium-3, acetylacetonate, and 1-dodecanathiol, and I expose them to 2 different periods while heating them, a vacuum period and a nitrogen gas period, in order to synthesize these nanocrystals to get that core ligand stabilizing ligand structure. And then what I do is I have all these things together, but it's got a lot of organics. How do I know where my nanocrystals are? How do I know if something's just specifically a solvent? What do I do? So I have to clean them, and I clean them by using a centrifuge tool, which got a brand new one in our lab. It's super nice. And basically I put them into these centrifuge tubes, and I put them in opposite sides so they spin, and then the nanocrystals are a denser material, so they'll pull out and form these little pellets. As you can see in that bottom right picture, that black pellet you see in kind of all of that red opaque solution, those are my nanocrystals that I will further use. So then what I do is once I have that pulled out, I redissolve them in chloroform, the nanocrystals, and then I subject them to drying via N2, just nitrogen gas. And then I characterize their absorbance. I adjust their absorbance to get it to a very specific concentration I want that I can use to test on fish that won't kill them. So continuing, I have this nanocrystal now that's adjusted to my specific concentration, but it's not soluble in the aqueous phase. So fish live obviously in an aqueous solution, that's how they thrive. So I have to be able to figure out how to get my nanocrystals to mimic that. So what I do is I perform a ligand exchange. And the ligand exchange, I do this so CIS is soluble in the aqueous phase. So I take my ligands I had on the outside that were stabilizing the core, and I replace them with other ones that are soluble in aqueous solution. So then after that, I do size exclusion chromatography, which is basically just a tool where I put this newly ligand exchanged nanocrystals in order to flush out any other organics that could kill the fish that wouldn't be the nanocrystals. I can flush them out by using size exclusion chromatography, which you can see actually in the very far right picture. That's a little bit of that's what my column looks like. And if you can see, it's kind of faint, but the little orange part is the actual nanocrystals that are falling through the column. And then after that, once I adjust the pH and everything, and it's all, 7.4 normal temperature of water, not temperature, pH of water, I start breeding my fish. So I breed embryos, zebrafish, from Dr. Lassiter's lab actually, and I collect my embryos, and I then collect data on them by exposing them to specific increments at specific molarities of my CIS nanocrystal aqueous soluble solution. So some main results and future steps of my research is we found that CIS nanocrystals are produced with a very tunable gap that fluoresces. As you can see in the previous pictures, they fluoresce orange when they're in their final state. And the methods I'm the second person on this experiment, and I've pretty much honed down on the methods we're going to use in order to collect more data and how to synthesize nanocrystals and how to go through ligand exchanges. So our next step is just tons of data collection, tons of breeding fish, tons of getting, repeating different trials in order to get enough data to be able to publish. And the whole point of this is to determine the toxicity of our CIS nanocrystals to see if they would be a cheaper and better alternative to cadmium. So why is this important? Well, our environment is kind of collapsing before our eyes. We are doing many things to perpetuate and to further along climate destruction. As you can see, these are 2 pictures of chemical waste spills in water and how chemicals and how different technologies we are using is killing our environment. So toxicology is an incredibly important field, especially now. It's something that really needs to be talked a lot about, especially when it comes to research methods. And a reason that I hypothesize CIS would be a very good alternative to the hard metals like cadmium and selenium that are normally used is I think that from the data I've gathered and will continue to gather until it's publishable, copper is a more environmentally conscious metal. It's not as harmful to humans. It's not as harmful to the fish. It could be better on the environment itself, and we're not releasing toxins into the air. It's also cheaper than cadmium and selenium, which is just another added bonus to that. So that is my presentation. If you have questions, you can always shoot me an email about this. So I hope you all enjoyed and have a great rest of your day. If I can figure out how to stop recording.